we are still talking about the liquids which are viscous, and today we will be talking about what is happening when we take a body, something, a physical object, like a bacteria, or hopefully when we will be allowed to go back to the beaches and swim in the lakes or oceans, then that will be us. And this physical object moves in the viscous fluid. When it is moving in a viscous fluid, it's obvious that the material in which we are moving, or this experimental object is moving, will experience certain resistance. And in physics, that means that the liquid in which the body is moving will exert a force on our body, and therefore it will slow motion of our body. And we know all that when we are swimming in the water, we have to spend a lot of energy in order to overcome the resistivity of the water. So I will start with the quite important, particularly for biological application, but also for fundamental physics, problem of a motion of a body which is very, very slow. Talking about the viscosity on the previous lecture, I mentioned that there is a number called Reynolds number, which measures the difference, a ratio between the inertial and viscous forces acting in a problem on our body. And what I will be discussing today is a motion of a body in a liquid when the Reynolds number is very small. So we have now the picture. We have a viscous liquid, and we have a body, which for the sake of simplicity, I will consider now to be a sphere. And that sphere moves with a certain velocity in the liquid. The flow is laminar. That means that the lines of a current, of a velocity of fluid, are continuous and do not form any vorticity, or there is no turbulence around that body. And the force which is acting on that body from the side of the fluid, so to say, I will denote it as a F with a little index D. And that is the red arrow on my picture. The sphere has a radius R. And we would now attempting to figure out what actually is that force, how the liquid acts on the moving body. And experimentally, people learn that for small Reynolds numbers and for not particularly high velocities, this reaction force Fd is proportional to the velocity. When the motion of the sphere becomes faster and faster, then this resistance force will change and will depend, for example, on the square of the velocity. And this velocity, this force for the higher velocities is of great importance for the engineers who are, for example, trying to build an airplane or a missile, or even when they are building up the very high buildings. I do remember that in the 70s, in 72 and 73, when I was in the United States, I visited Boston, and I was completely flabbergasted seeing in a center on the bank of the Charles River a huge building which was a headquarters of a giant insurance company, Hancock, and the skyscraper had most of its windows actually replaced by the wooden panels. And they had the problem for quite a long time that the heavy winds blowing from the side of the ocean were popping the windows out of the building, and that was a construction error. And it took a long time for the engineers to figure out what to do and to find that the John Hancock now has the normal windows. But we will be talking today about the motion with the relatively slow velocities. So this resistivity force is proportional to the velocity. So we are actually only interested in what is the coefficient of a proportionality is sitting in the front of it. And obviously, from a very simple thinking about this, it has to depend on the radius of the sphere, it has to depend on the viscosity of the liquid, and of course it has to depend on the density of the medium in which our sphere is moving. So if I denote the radius of the sphere by capital R, viscosity as always is a Greek letter eta, and the density is rho sub 0, then following our previous discussion of a dimensionality analysis, we assume that this proportionality coefficient is proportional to the certain power of radius, to another power of the viscosity, and to some other power of the density of the air or the liquid, rho sub 0. And there is also probably some numerical factor which I have denoted as a little phi. All right, now velocity has a dimension meters per second, and the force is dimension of a newtons. So it is easy to figure out what is the dimension of that coefficient which I had written in the square bracket. All right, so if I now apply the dimensionality analysis, knowing that R is measured in meters, eta is measured in poise, and rho is measured in kilograms per meter cube, then recalling what is actually dimension of a poise, we easily find out that these coefficients A, B, C have to be equal 1, 1, and 0. Then this, so let me repeat that these coefficients, this dimension, these coefficients A, B, and C are 1, 1, and 0. And then the formula becomes pretty simple. The force is proportional to the radius, to the viscosity, and obviously to the velocity. The only remaining missing thing is that numerical factor denoted by phi. And as you see, this is the beauty of the derivation of expression using this dimensionality analysis, because we don't need to do any complicated mathematics, and we got the exact result. The coefficient phi can actually be calculated, and when one uses this mathematical equation which describes the property of viscous fluid, these equations are called Navier-Stokes equation, and I believe I mentioned already, and they are probably the most complicated partial differential equations which in a classical physics have been used. Then we can solve the problem we are discussing exactly, and then this coefficient phi turns out to be equal 6 pi. And therefore, the force acting on a sphere which moves slowly with a steady velocity v through a viscous liquid is 6 pi times its radius times viscosity, and this is called a Stokes law. We should keep that in mind because the Stokes law, we will be using it for next few slides on solving interesting problems. All right, and again, let me repeat that this analysis is applicable only when the Reynolds number, which I had written again, is now really small. That means it is less than 1. All right, so let's try to solve now the following simple problem. And the problem is the following. We have a container, which I had driven as a cylinder. And inside of that container, we have a liquid. And there is a sphere with the radius r and with the build-up of out of the material with the density rho. And the container is filled up with the liquid with the density rho sub 0, and the liquid has a viscosity coefficient eta. And this is all in a gravitation field on the Earth. Therefore, the ball is slowly, very slowly moving down that cylinder. So this will be the same situation if instead of having a ball falling down in a cylinder, I had a flow of liquid around the non-fixed ball, and that will be precisely the same situation. So now we have the diagram of forces acting on our body. There is a one force denoted by a red arrow, which points downwards, and that is the weight of the sphere. And there is another force which we discuss, talking about the Archimedes Principle, and this is a buoyancy force, which I have denoted as a green arrow, and which is pointing upwards. And since the ball is moving slowly and steady downwards, then there is this resistivity force Fd, which is governed by which is given by the Stokes law, and is proportional to the velocity. So we have three forces acting on our body, and we can now try to analyze its motion. And as we know from the Newton's second principle, the equation of motion for such a body is given by a second law, as I said. It's a mass of the body, which I have written as a script m, acceleration times acceleration, and that is equal to the total force acting on our body. The total force acting on myself is the sum of those three forces. Acceleration is what I would like to calculate, and m is the mass of the body. Well, what is the mass of that object? It's the volume of the sphere times the density. So the mass is equal to the volume of a sphere is a 4 pi divided by 3 times the cube of the radius times the density. But this is not correct. It is not correct, and that actually is why a simple problem which I have mentioned some time ago on probably our first lecture about what is the acceleration of a balloon which is marooned, and then somebody cuts its rope and the balloon is starting, with what acceleration balloon is going up, because when the sphere moves downwards in the liquid, then the liquid also has to move. Because if the ball moves a little bit downwards, it doesn't leave behind a vacuum, a void in the liquid. If the ball moves down, then there must be a motion of a liquid which fills up the void above it, which was formed by the fact that the ball is no longer there. And that is a very beautiful chapter of mathematical physics, how to calculate this, what is called the effective mass. What is actually a mass of an object moving in a liquid? And the result is that it is equal to the bare mass of the liquid plus what the people called associated mass, which I denoted by a little m, by capital M, but not script M. And the important point is how we can calculate this associating mass. And for a sphere, this is relatively simple. And it is, if you think for a while about that, what is happening when the ball moves a little bit downward and how much of what is happening above it, then you can easily convince yourself that this is just 1/2 of the volume of the mass of the liquid, which have to fill up the void behind the sphere. That simple formula, that this associating mass is just 1/2 of the mass of the liquid, which was previously in the region occupied now by our body, is only possible for a sphere. And as I said, there is lots of very beautiful mathematical works devoted to deriving this expression for other objects. And it's done exactly analytically. There is a formula given for ellipsoids and for cone, but for the other bodies, we have to restore to the numerical calculation. And nowadays, that's relatively a conventional procedure, for we have the huge machines, we have computers, and there is a method in mathematics to calculate, to solve the Navier-Stokes equation with the moving boundary, with the moving ball inside of the liquid, which is called the finite elements method. And it is a very powerful mathematical method which allows us to calculate this resistance force, as we will see in a moment exactly. And what will be what kind of the driving force we have to, for example, apply to the car when it moves on the highway, because it experiences the resistive force of the air, and of course also there's a problem with the tires, but let's not talk about it at the moment. And this finite element method is so powerful that we can calculate the shape of the car, which will lower the effect of this resistivity forces pretty well. And that is why most of the modern cars are very similar to each other, because the mathematics gives an optimal shape for the given volume of the car. But we will be talking about the sphere, so we are now looking at this equation when the motion is stationary, is steady. When it's steady, then it moves with a constant velocity, and therefore the acceleration is equal to 0. Therefore, the left-hand side of this equation is equal to 0, and the equation of motion for that falling ball is just that the total force is equal to 0. So since the total force is equal to 0, then out of my diagram it follows that the resistance force Fd plus the buoyancy force must be equal to the weight. So now if I put the buoyancy force on the other hand of my equation, and then I use the Stokes law for F sub d, And that is the equation which gives me the velocity of a falling body. And as you see, this is a coefficient which is depending on the size of the body. And actually R squared is, well, there is a pi missing. But if I will multiply this ratio by the pi upstairs and downstairs, nothing will change, but the pi R squared will be just the cross-section area of our ball, and is proportional to the gravity acceleration and to the ratio of the densities. So we have the exact expression for the velocity with which body is steadily falling down in the liquid. So let's solve a current example. We consider a droplet of a liquid with a density similar to the density of the water and a radius 10 to the minus 5 meter, which is falling in a gravity field in the air. So the radius is 10 to minus 5. The density, I assume that the density is slightly bigger than the velocity of the water, and the density of the water is given here. So the velocity with which the particle falls down is easy to calculate from the previous derivation, the previously derived formula, and the result is a factor 2.5 times a 10 to the minus second meter per second. So that is the velocity, and having calculated the velocity, I can check what is the Reynolds number, and the Reynolds number, we were working under the assumption that the Reynolds number is less than 1, therefore we check whether this is correct, and the Reynolds number which I have calculated is really very small. So everything is fine, and I also can calculate the value of this Stokes force, and that Stokes force turns out to be 10 to the minus 11 of a Newton. And I took this because the droplets of a liquid containing the viruses of SARS-2, those droplets which we cause by coughing or sneezing, are basically of the similar radius, 10 to the minus 5 second, and the density is slightly less than water. So you can now do the calculation, and if the density is slightly less than water, then the droplet goes up and floats in the air. And if it's only slightly larger than water, then it falls down. And as you see, the velocity is 10 to the minus second meter per second square. So those droplets fall down to the earth in a time of order of minutes, and therefore there's very little danger that when you are missing somebody on a street, then the cloud of the viruses around that person will actually reach you. All right, so that was one example. And now I would like to tell you about the application of a Stokes law in fundamental physics. And therefore I will be talking about the Millikan experiment. Millikan experiment is one of the most fundamental experiments in contemporary physics. It is the experiment which is basically 107-year-old, because the main results were published in 1913. And that was an experiment done by American physicist Robert Millikan. This is his youthful portrait over here. And that was the experiment in which Millikan measured the value of a unit charge of electricity. We know that there is one of the fundamental constants in physics is the value of elementary charge of the electron, which is the unit charge in the nature. all the other electric charges in the nature are just the some even numbers times the number of the times the value of the charge of the electron. And at the turn of the 19th and 20th century, people were still hesitating whether there is actually such a thing as a unit charge. And there is a physical object which has this unit charge on it. And, and eventually they started to accept that notion, but they had to calculate or measure the value of that elementary charge. And the experiment in which for the first time it was measured was Millican experiment. And that is the drawing of that experiment. The experiment was pretty simple. There was a container to which droplets of oil of different sizes were produced by some device, a little pump. And those droplets of oils were falling down, and they were falling down until they reached a plate, a metal plate with a little hole in it, through which only very few of the drops could pass. But that metal plate was actually an electrode. It was connected to a battery, and there was a lower plate which was grounded, and there between those two plates there was a electric field, a rather strong electric field of the voltage of 1,000 volts which had been applied. And now the droplets, and that was observed from a side by a microscope, and by changing the voltage, Millican was able to observe what is happening when the droplets are falling down in the electric field. By touching the electrodes up, they were charged. And when they were charged, they carried the electric charge on them. So when they were falling down through those plates, which was essentially condenser, then they experience, in addition to the gravity and buoyancy and then the Stokes force, they were also subject to the electric force. And the sum of those forces was either zero or not zero. If the electric field was too strong, then it was too weak, then the droplets were slowed down with respect to how fast they were falling down without the electric field applied. And when tuning the voltage, Millican was able to adjust the field such that the droplets was approximately stopped. They were not falling down. If they were not falling down, then he knew that the sum of a buoyancy, gravity, and Stokes force must be equal to the electric force. And since the electric force is proportional to the charge on which it is acting, then he was able to calculate what is the charge on a droplet and establish that on all droplets, the charges were proportional to this elementary charge, and he measured. This is the picture of the original Millican experiment. As you see, this is a remarkable, simple experiment to discover one of the fundamental constants of nature. And if you compare it with the size and complexity of the contemporary experimental apparatus, you certainly we will have something to think about for a while. And Millican had done these experiments. The experiment was extremely successful, and well, it was associated with certain peculiar story, because actually Millican was doing this experiment with his PhD student, and there was some complication with why that PhD student was not on the paper, but he wasn't. So the Millican got the Nobel Prize, and Millican measured the value of the unit charge, E sub m, which is 1.59 times 10 to the minus 9 of the Coulomb. Coulomb is the elementary charge, is a unit of the electric charge. And at the time of the Millican experiment and until last year, the Coulomb was defined in a complicated way because the Coulomb was defined as the amount of electricity which is carried by a steady current with of 1 ampere over the time of 1 second. And in addition, the 1 ampere was defined as a force which was acting between 2 wires with a given length and with given cross-section. And that was very imprecise definition. And last year, eventually, the international organization which is in charge of keeping track of how the various fundamental and not so much fundamental constants are in physics and engineering defined. This is called the System International. That institution decided to change the definitions of and define that the Coulomb, that the elementary charge is exactly that much of electricity. This is the exact value. There is not, and this is the unit. And we know that this is correct because that is the unit of a charge of an electron. And all electrons have the same charge. So that means that the Coulomb is defined as the certain huge number of the charges of the electrons. And since last year, we do not have any need of defining any physical constant we use by employing complicated structures like the unit of a meter, which was in Sèvres, Paris, and something, because all the physical units can be defined by means of the fundamental constants of nature. This is electric charge, speed of light, Planck constant, and mass of electron. And that is enough. And all of them can be measured in a microscopic way. Unfortunately, we still have a problem with how to construct a proper unit for a degree of a temperature, but with that we will be talking about slightly later on. So this beautiful Millikan experiment is the use of the Stokes law. Okay. We will now be discussing something which is of your great interest, because when I was visiting Nensky Institute years ago, I learned actually that the Institute has a tremendous number of centrifuges. And we will be talking for minutes about the centrifuges. And on that picture, you have a history of a centrifuge. On the left side, there is one of the very first centrifuges commercially built, engineered by a company to sell. And that is the centrifuge which was used in the dairy industry by those who were busy with extracting a fat from the milk. Probably already in ancient times, people learned that by rotating a container with the milk, they can separate a part of a fat from the milk. And this is used until today. And if you go to the supermarket, you have on the shelf a milk which has a different percentage of a fat in it, 2%, 3.5, and I don't know how much. I believe they are on commercial, there are only these two which are sold, but probably they can produce the milk with no fat at all. And this is a centrifuge. And the first centrifuge of that sort was built by a fellow with the name Antoine Prandtl, and he was an engineer, German engineer, but it was eventually his father brother who makes a fortune on making those centrifuges. And the centrifuges were kind of an engineering construction. No much theory was about what is actually how the centrifuges work until the Swedish physicist Svedberg, who had developed a theory of a centrifuge, and he built a first modern centrifuge, which is in the middle of the picture. And the reason why he needed the centrifuges which were called ultracentrifuges, because already in the 20s of a previous century, Svedberg was able to rotate his centrifuges with the rotation which was about the 60,000 revs per minute, and that corresponds to the gravity force of the order of 500,000 of acceleration of a gravity. Svedberg built up his centrifuges to study colloids, and he got the Nobel Prize for it. And today's centrifuges, which you have in institute, are basically what had been technically developed from the Svedberg centrifuge. And on the right, you have a centrifuge which we do not know exactly how it is built. So all my drawings and a few words about it is what you can learn in the books. It's the details of the construction of it as are known. These are called SIPE centrifuges, and we will be talking about them in a moment. So how the centrifuge works. Let's recall from the elementary physics course what is happening when we have a body which moves on a perimeter of a circle. The body, it rotates with the frequency omega, and it is at its velocity is constant, but the direction of the velocity, and velocity is a vector, is changing because the value of that red arrows are everywhere the same, but the direction changes. If the direction of a velocity changes with time, then the motion of that body is not a steady motion, it is the motion with acceleration. And if the body moves with the constant frequency around the circle, then this acceleration is constant. So the motion over the circle is an example of a motion which has constant acceleration and not what follows from this picture is that this acceleration is directed towards the center of the circle. And therefore I call it A with sub R to denote that it's a radial acceleration. And the fact that acceleration directed towards the center is actually a physical fact, because if the body moves over the circle, there must be a force which holds it on that circle, and that force must be towards the center of a circle. And again, a second law of Newton tells us that the force is that the acceleration times the mass of the body is the force acting on the particle. All right. There is something which you must have remembered from the high school, that if the body moves around the circle with the constant frequency omega, then the value of the velocity is constant also, value, but not the direction. And the value is equal omega times the radius of the circle. And the radial acceleration is proportional to the omega square times r, and that you can easily, without even remember mathematics of the school, from the high school, learn, because the acceleration must be velocity, it has unit velocity divided by time, and omega has a dimension of 1 over time. So if this is the velocity, then the acceleration must be omega square over r, because that's the only time unit which is in our problem. So we now know the velocity, we knew the acceleration, and therefore the gravity, the weight, the force acting on the body moving on the circle is the gravity, or the force which holds it on the orbit, minus the radial acceleration. And therefore, I'm sorry, and now we will continue, but before this, let's apply our formulas to the problem which is frequently used in biological application, namely to what is called the sedimentation. We have a container which contains a mixture of a liquid with very small particles. There are lots of very small particles in that liquid, and it's more or less homogeneously distributed to the liquid. And we put it in the gravity field in some force which acts on those particles in direction on my picture downwards. So when we wait for a while, then we know from the experiment then the situation will change, and that most of those tiny little particles will found itself on the bottom of the container, and the liquid will be basically clean liquid above. That process is called the sedimentation, and I will try to find out with what velocity that will happen. The force, if the sedimentation is happening pretty slow, then I can apply our previous analysis about the Stokes force, and therefore the force which is acting on the particles going down to the bottom of the container is the force of the weight minus a buoyancy force. And we know from the previous discussion that this force F sub B is just proportional to the velocity, and I written here that this proportionality coefficient is small f. From a Stokes law, we knew that F is 6 pi radius times the viscosity coefficient, and the weight is the mass times the gravity. The buoyancy force is as the same, so I can rewrite it a little bit, dividing and multiplying by the density of the particles, and then the buoyancy force is the ratio of the is the ratio of the densities times the mass of the particle times the gravity. So this equation, which we use deriving a Stokes law, now assumes the following form, and I can solve it for the velocity, and then the velocity of sedimentation is having a very beautiful and simple form, is a mass of the particles times the force divided by this coefficient f, and in a bracket we have a 1 minus ratio of the density. All right, that is again the picture which I had in mind. So we have this sedimentation velocity derived, and for some reason my pictures show up in the reverse order. I'm sorry for it. And we will now have another glimpse on the factor f. The f we knew from a Stokes law how much it is, but we can look at it differently. And that will require a small discussion about the microscopic view of a fluid. We have the liquid, and the liquid contains the particles. It's built up from a very small particles. And those small particles, they move at random. They move with different velocities in different directions, and and they occasionally collide with each other. And if we look at one of those particles, if we sit on one of those particles and follow its motion, we soon will find that the motion of the individual particles of the liquid can be described using a model which in theoretical physics and mathematics is called random walk, and in the courses of mathematical statistics is called a drunken sailor problem. Why it is so? So let's think about it for a while. And imagine you have a street and there is a bar out of which a drunken sailor comes out. And now he is now on the street, and it's the one-dimensional street, so he can move on the left or right. The particle in the liquid can move left, right, up, and down. So the situation is slightly more complicated, and also can move in the directions with different angles. But let's first discuss the sailor on the one-dimensional street. So he can move left or right. And let's make an assumption that he is always moving either left or right with the same probability, that he chooses completely at random whether he will go left or right. So he makes a step right. He is on the right, and now he has to make the decision what to do next. He can again move either left or right. If he moves left, he returns to the doors of the bar. If he moves right, he moves farther away. And if he moves far, and whatever he chooses to do, at the next place, he again makes the same decision to move with equal probability left or right. So it doesn't require a lot of argumentation that on an average, he will not move very far because he moves left, right, left, right. So basically, he will not depart from the bar. But if we mark on this street with a pencil or a chalk the places he visits, we will see that he will be departing very far from the bar on the one side, on another. So we can look up on the region he explored during his random walking. And the size of that region have an unusual property, namely the average square of the size of that region grows linearly with time. And the coefficient between this average square, the size of the region he explored, and the time is called the diffusion coefficient and is usually denoted by a capital letter D. And the factor 2 comes out from detailed analysis of that problem. So we have this relation. And that relation is very fundamental in many applications. For example, a huge industry, which is a cosmetic factory, particularly those people who are in the business of fragrances, they are living on the fact that the region explored by the moving particle is proportional, its square is proportional to the time, and therefore the cloud of a smell around the person using a perfumes stay with that person and does not disperse very quickly. So when the person enters the room, we see it and we hear it much earlier than we smell it. All right, so that is the formula. And so we may now ask the question, what is the kind of average velocity with which this region on a sidewalk is explored by a drunken sailor? And that average velocity is a size of that region, which is the square root of the mean square, divided by time. So let me call this square root of this mean x squared by a letter L. Therefore, the average velocity is L divided by T. And using this formula, I can easily see that the diffusion coefficient D is just the product of the L times V with bar. What is the V bar? This is a mean velocity, because if I have an object which moves with the average velocity V, that its mean velocity is just the average velocity divided by 2. So I have a very beautiful formula for a diffusion coefficient. And now, if the particle moves, and on average, it moves with the velocity V bar. Therefore, the force which this particle is acting on this particle, this Stokes force, is the coefficient F times V bar. Well, then I can calculate what is the force, work done by this force on a particle which moves the distance L. Work is a force times a distance, so the work is FB times L. So when I do this multiplication, I find out that this work is equal to F times diffusion coefficient. But if I spend some work on it, then of course I have to lose some energy on it. And this work done by the particle is done on the expense of the energy, which in this case is just the kinetic energy. And the kinetic energy is the mass of the particle times the mean velocity square divided by 2. If I compare these two expressions, I find out that my coefficients F is equal m mean velocity squared divided by 2d. All right, so this is another glimpse on the coefficient F. From the Stokes law, I know that F is equal 6 pi eta r. Great. Then I can put it there, and mean energy of a particle in the system is what in the kinetic theory of gases is called the temperature. So this is nothing else than the temperature of the liquid. And then I find out a formula that the diffusion coefficient is related to the viscosity of the liquid. Diffusion coefficient is a temperature divided by the viscosity coefficients and times the radius of the particle. And that is a fundamental expression from the microscopic theory of liquids and gases, which is called the Einstein-Stokes law. And as you see, it relates the diffusion coefficient to the viscosity. The viscosity was something related with the systematic motion of the liquid. It was the resistivity of the one layer of liquid with respect to another. But the coefficient F is, and that was the coefficient F. And the diffusion is something related with the size of a cloud explored by the drunken sailor. And those quantities are related with each other. That is the very simple and beautiful formula. Actually, it's in fact one of the very first formulas like this, which have been discovered in physics of many-body system, and they are related to very general theorems, which are called the fluctuation dissipation theorems. All right, so examples. Consider now a motion of a hemoglobin particle in water at the room temperature, which is 27 Celsius, and that is 300 Kelvins. And these are the properties, the constants which we need to know. The diffusion coefficients of a hemoglobin is 6.3 times 10 to minus 11 meters squared per second. Mass of the hemoglobin molecule is 10 to the minus 22nd kilograms. The density of a hemoglobin is as you see, it's slightly larger than water. Is 1.35 times 10 to the third kilograms per meter cube. Density of the water is of the order of 1. And the gravity acceleration is 9.8 meters per second squared. So let's now do the calculation. The friction coefficient F is kT over diffusion coefficient. So I use this number and I can calculate the friction coefficient. And it turns out to be 10 to the minus 11, actually almost 10 to the minus 10 newtons times second divided by meter. And sedimentation velocity is then 10 to the minus 7 meters per second. And that was how fast the hemoglobin is sedimenting in water. And another example is about the proteins. I would like to look at the proteins at the same temperature in water. The density is slightly different, and the density of proteins is very similar to the density of hemoglobin. And I will now look up at what is happening with this mixture of water and protein in the centrifuge. And the centrifuge's acceleration is 10 to the 6 meters per second square. This is the Swedberg's-like centrifuge. And then the measured velocity of a sedimentation is 10 to the minus 6. So I can, out of this, get the number. I can turn around my equation and I can calculate the mass of the protein molecule out of this formula. And the mass of the formula turns out to be 10 to the minus 22nd. So basically, that is what the centrifuges are used in many labs. They are used to calculate the masses of the particles which are suspended in some liquid mixtures. All right. And the third application of a centrifuge is a nuclear centrifuge. That was this third picture. And this is a photograph of a cascade of a centrifuge, which are used to produce enriched uranium at Pinkerton, Ohio, in the United States. There's plenty of photographs in the internet about the same arrangements in the Iranian factories. But I mean, we don't know what is happening there. We know exactly what is happening in Pinkerton and in other places in the United States. So what are those centrifuges? These are centrifuges which are peculiarly built. They are very thin steel, particular kind of a steel tubes, which rotates at enormous frequencies, and they are used in order to separate by a centrifuge principle the two isotopes of uranium. Uranium in the Earth crust is 99.3% of it is the uranium-238, which is completely harmless substance and which is not good for any nuclear applications, plus less than 1% of uranium-235. And this uranium-235 is the isotope which fits, and when hit by a neutron, it splits, the nucleus of that isotope splits into pieces and is emitting 2 neutrons. So if we have lots of the uranium-235 nuclei in one place, then it is sufficient to hit it with 1 neutron, then 1 nucleus splits and produces 2 neutrons, which split additional 2 nucleus, and then we have 4 neutrons, and the 4 neutrons split the 4, and so forth, and that's what is called the chain reaction. So the whole nuclear industry, whether for production of materials needed in nuclear reactors or that which is used for building of atomic bombs, then they have to have the uranium, they are built from uranium-235. And therefore we have to enrich the uranium. We dig out the uranium from the Earth crust, and in some chemical and other processes, we have to separate this unusable uranium-238 from the uranium-235. Actually, uranium-238 is also of some use, particularly for generals, because it's very heavy metal, and therefore it can be used in the projectiles to cause them to be very lethal, but that's another story. So this is how that centrifuge works. It's a drawing of that centrifuge. We have the 1 inlet and 2 outlets. Through the 1 inlet, the uranium, the mixture of the uranium isotopes is pushed into the centrifuge. Actually, it's form of a gaseous substance, which is the uranium-6 fluoride. And it's the substance which is pretty yellow. And you might have heard the stories of the nuclear smuggling of yellow cake. That's something related to the production of this hexafluoride of uranium. And this gas is pushed into the very fast rotating column, in which, in addition, there is a huge gradient of a temperature. The lower part of the centrifuge is hotter than the upper part. And because the isotope 38 is heavier, then it, by rotation, by the principle of a centrifuge we discussed, is thrown out to the walls of the container. and by the convection currents, due to the difference of a temperature, is moving up and is scooped via these two pipes out, and the enriched uranium is lighter, so it stays in the middle of the, close to the middle of the centrifuge, and is sucked up out of the container. Unfortunately, the difference of the mass is very little, and therefore efficiency of that centrifuge is very low. And therefore, the enriched uranium, which goes through this pipe, is not used, is pumped into another centrifuge, and then into another centrifuge. And at each step is enriched a little bit more, a little bit more, and a little bit more. And this whole process is extremely technically complicated, and that construction is called usually ZIPPE centrifuge, and it's a remarkable history. When the nuclear industry was being built in Germany and the United States during the Second War, the German physicists, the fellow named Seebeck, had invented the centrifuges and thought that it is probably possible to separate isotopes by means of a centrifuge. But the Germans were not able to build atomic bombs for another reason. They made a mistake in the other aspect. But anyway, they had a beginning of a theoretical work on those centrifuges done. And the Seebeck and his colleagues was captured by the Russian army, and they were sent to this town of Sukhumi in Soviet Union. And then there was a huge laboratory run by German scientists, whisked from the occupied Germany by Russians. Not, the other part was whisked by Americans. And the head of that business was a kind of extremely interesting character, certain Manfred von Ardenne. But anyway, the work on the centrifuges was going on there very slowly. And then there was in one of the prisoners of war who was working there was an Austrian, Gerhard Zipper, who made a technical breakthrough. He invented how to construct the centrifuges, which will be able to move at something like 90,000 of revs per minute, and do not blow apart. And in a very unusual way, Zippe was permitted to leave Soviet Union in the 50s, and he somehow migrated to the West Germany. The head of the laboratory, Ardenne and Seebeck, they went to East Germany, and Zippe went to the United States, and he, at the University of Virginia, built up the first centrifuge of that form. He was not allowed to take out of the Soviet Union any notes, but he just have remembered how he built up this device. And at that stage, Americans who were not using a centrifuge to enrich uranium, they used the diffusion separation, which is shown here on the lower part of the drawing, and which was very expensive and energetically very inefficient. Then they basically confiscated the Zippe model built up at the University of Virginia, and Zippe has left the United States. He went to Germany and set up a company called Urenco, which was and is enriching uranium for nuclear reactors. And then for that company, he built a really efficient centrifuge. And what are the details of that construction is strictly secret, However, there is a considerable amount of espionage stories about and spies who were trying to get those centrifuges, and this is a story which you know from the newspapers, so I'm not going to talk about it. But that is a centrifuge. The centrifuge is about 5 meters high and move at this tremendous speed and eventually works. And of course, it's nowadays run by microcomputers, and that was the reason why the Iranian nuclear project some years ago was sabotaged by hacking the computer system of those centrifuges with the virus, which was called, I believe, Stokes, but I'm not sure. All right, so that's about the centrifuges. And we are now going to another chapter of a liquid physics, which is also very important in application. Namely, we are going to talk about the liquid surface. We all know that all the bodies in real world have the surfaces, and the liquids also have the surfaces. And that picture shows that the surface on a liquid can carry on it various form of waves. And the reason is why. How come that what is happening on the surface of this liquid, that on the surface of the ocean, this is a picture of the ocean, you have such a beautiful and complicated waves. And this is another picture of a surface of a liquid made from the size. And as you see, we have a liquid below, and we have the undulations on the surface. And something which you cannot really see is that this liquid does not look like it's sharp. It looks like it has a certain thickness. And that is another view on the surface. When you drop something into the liquid, you have a concentric waves which are propagating on the surface. So if you have such undulations of the surface, the waves on it, then there must be some kind of a force. So which is, if the surface goes up, it takes it down. So it is a force which is a driving force for those oscillations. And that driving force is an important property of the liquids, which is called the surface tension. And the waves on the surface of the liquids are called ripples. Okay, so this is the picture of the liquid surface, which you usually see, for example, in your teacup. You have a liquid in the middle, and you have a air up there. And if you look very closely to the side of the glass, you see something which is called meniscus. You see that the surface of the liquid goes a little bit up in the glass. But if you will, for example, look on something which is for all, which I believe is now illegal, if you look at the liquid mercury in the glass, you will see that it is not going up on the walls, that it curves downwards. So this change of the shape of a liquid surface in a contact with a solid wall is called the meniscus. And we have two kinds of a meniscus, convex and concave, depending on the properties of the liquid and also on the properties of a solid wall. But if when we take a microscope or a good magnifying glass, and if we look what is happening close to the surface of the liquid, then we see that here is the liquid, which consists of many, many, many liquid molecules. But then we will go up. We all over the sudden see that this is not an empty space. it is space where we do have much less, but still molecules of the same liquid. So if I plot a density of a liquid, this is a direction of z, then if I look up at the density of a liquid, then I have a density which I can always make equal to 1. And there is a more or less constant density. And then we are approaching the surface. And the density all of a sudden drops. But it doesn't drop very sharp. It drops. And then if we go far away from the surface up, it will be again equal to 0. So the density profile in the liquid close to surface is given by such a function. And there is a certain width here, and that width is important. If we have a curve like this, then let's forget for a while of this drawing. Let's do the following experiment. We take a container of the liquid and we immerse into it a frame, a metal frame. And one side of that metal frame is movable. Is a tiny little metal pipe, for example, with a length L, and we immerse it into the water. And when we move it out of the water, then we see that there is a thin layer of the water which is formed in the frame between those 4 edges. If you look from the side, then this is this lower part of our frame, which has a certain thickness. And there are 2 layers of the liquid which fill up that frame. The area here is denoted by A. And this wire, this movable wire, has a certain weight, and it doesn't fall down. What that means? That means that there must be a force acting on it upwards, which holds it in a given shape. But there is another force which comes out from the fact that there is a density profile of the liquid. Here is a liquid, here is an area where there are very few liquid atoms, and such a thing is called the vapor of this liquid. And there is an additional force which acts along the interface, this surface, which I denoted as a W2. So the total force, which keeps that sheet of liquid in place, is sum of these 2 forces. And because there are 2 layers of the liquid, then this force is twice the length of that wire, and there is a certain coefficient which tells us everything about the property of the liquid. And that coefficient, which I denoted as a gamma, is called the surface tension. The force here is proportional to the length, and it balances this thing. Units of gamma are newtons per meter. Okay. And we can measure those things, and I have written here the values of the surface tension coefficient for various temperatures. For example, ethanol and oil and water. And water I had written for various temperatures, and as you see, it goes down with the increase of a temperature. This is the oxygen, liquid oxygen. Liquid oxygen exists on the very low temperature, minus 193 centigrades. And the copper, this one is a low temperature liquid, and a copper is a high temperature liquid. It has a tremendous surface tension at the temperature 1,000 degrees of Celsius when the copper melts. And that was the phenomenology of the surface tension. And we will be discussing what is the surface tension in some greater detail next time. And we will also use it for particular applications. And I hope we are on time. So thanks a lot.